Hey there, Adrian Rosebrock here from PyImageSearch.com, and today we're going to be digging into gradient descent with Python. Gradient descent is the workhorse of essentially every neural network. There's various forms of gradient descent. There's your standard vanilla gradient descent, there's stochastic gradient descent, there's mini batch gradient descent. All of these variations, though, they're essentially the workhorse. They are what power neural networks. That's how we're able to train our neural networks to learn patterns from our training data. So earlier in this series, you've learned about the concept of parameterized learning. We've discussed the concept of taking dot products between weights and biases and inputs, and then kind of creating this magic formulation of how to make predictions. The question is, like, how do we train a neural network? Like, how do we take these weights and update them in an iterative fashion such that we're able to learn these patterns and make confident, accurate predictions? That's what we're going to be digging in here today. And this tutorial here on gradient descent, as well as the next one on stochastic gradient descent, this is where I want you to spend the vast majority of your time. I would really allocate 1 to 2 hours to studying these tutorials if you're new to neural networks and deep learning, because the the intuition you get here is absolutely critical in understanding neural networks as a whole. This entire training pipeline, you need to internalize it, you need to digest it, you need to have it memorized like the back of your hand, because every formulation of neural networks is trained with variations of gradient descent. So here's how I suggest you go about studying this lesson. I want you first to pause this video, and I want you to go to the text version of this article. I want you to read it in its entirety. I'm going to discuss topics such as weights and biases. I'm going to discuss the concept of global minimums and local minimums. I'm going to discuss how gradient descent works, how, if we place our little optimizer here at the top of the bowl, it's supposed to be able to find its way to the bottom of the bowl using this concept of gradient descent. I go through the mathematics, the concept of treating every problem like a convex problem if it's not. Really important concept here is the bias trick, and I discuss the pseudocode for the algorithm. So go through this tutorial, read the text version of it first. It's going to give you a really detailed understanding and review of what gradient descent is, what its goal is, and a mathematical formulation of gradient descent. After you've done that, come back here and watch the tutorial, and I'm going to walk you through the code. I'm going to walk you step by step through what this code here is doing and how it implements gradient descent. But the caveat here is you're not going to understand my explanation of this code unless you've read the text version of the article first. So that's why I recommend read the text version, come back to the video, watch the video, and then go back to the text version and read it again. I want you to go through this material 3 times. I know that sounds redundant. I know that sounds like a lot of effort. But again, if you don't understand the concept of gradient descent, you're not going to be successful as a neural network and deep learning practitioner. You need this knowledge. It is truly that critical. And even if you get nothing else throughout PyImageSearch University, I want you to understand gradient descent. So go ahead and pause this tutorial if you haven't read the text version of it yet. Once you've read the text version, come back here and we'll start digging into code. So if you're this far, I assume you're done reading and you're ready to implement gradient descent. And we just have a single Python script review here, gradientdescent.py, and this is going to implement our vanilla gradient descent. Later in this series, and in fact, next tutorial is going to be on stochastic gradient descent. Then we're going to look at variations of gradient descent, and then we're also going to look at regularization terms and how we can make our weight matrix a bit nicer, a bit capable of making better predictions without overfitting. So I'm going to come over here to PyCharm. I'm going to open up our Python script, and let's get started. First function we have here is our training and testing split. So we're going to take our input data, we're going to segment it into this training set, which our model is going to learn from. It's going to take that data, make predictions on it, and update the parameters of the model in an intelligent way, such as it's going to make better predictions on our training set. Once we've completed the training process, we're going to take that testing data, which the neural network hasn't seen before, and we're going to ask it, hey, make some predictions on this testing data. Take the patterns you learned over here on the training data, and let's see how you do on the testing set. Let's see what your results are like. Let's see if you're making accurate predictions. Because ideally, what we want to see is high accuracy on both our training set and our testing set. What sometimes happens though is that we over optimize the training set, and essentially our neural network just memorizes what the training set looks like. Well, that's not very helpful because simply memorizing the data isn't going to enable you to make accurate predictions on data that the neural network has never seen before. So this is a concept called the ability of the model to generalize. We want our model to be able to generalize to data that it hasn't seen before. All that means is we want our model to make correct predictions on data that hasn't been trained on. That's all the ability of a model to generalize means. Just keep that in the back of your head. We have the classification report function that's just going to give us a nicely formatted report telling us how good of a job our model did at making predictions. And this make blobs function, this creates a dummy data set. So we're not going to start working with image data yet. We're going to create basically a 2D set of data in separate blobs, and I'll show you an example of that in a second. And our goal is going to be able to partition that data into two classes. We have matplotlib for plotting, numpy for numerical array processing, and argparse as our command line arguments. So I'm actually run this script now because I want to show you this output here. And this is what our data looks like. We have a 2D representation. This yellow class, this is one set of data, and then this purple class, this is another set of data. So clearly looking at this, you could draw like a linear line that separates these two classes. And our goal is to train a neural network that can predict that line. So if we imagine a line going like this, well, the data that resides over here will be predicted as yellow, and the data that resides over here will be predicted as purple. So we want to train a network that can do this automatically. How do we do that? The answer is gradient descent. So let's pop over here to our code. And if you, again, make sure you go into the text version of this article because I'm going to start using terms that if you haven't read the text article isn't going to make sense. But make sure you read the text version and let's keep going. We define the sigmoid activation function, which if you haven't seen what the sigmoid activation function looks like before, essentially looks like this little curve here at steeper here in the middle, and it kind of levels out at these asymptotes. So it has a value between 0 and 1. So you can kind of think of that as a rough probability. When you're at 0, your predicted value is going to be like 0.5. So that's your probability amount, like cut it right in half. And as you descend back down here, you'll get a probability value of 0. And up here is a probability value of 1. This is kind of like a surrogate probability value. That's how I kind of like to describe it. So if the output predicted value is greater than 0.5, then we'll set that value to 1. It'll be like a clamp threshold, being like, okay, predicted value greater than 0.5, that's going to be class 1. Otherwise, predicted value less than 0.5, we're going to clamp that down to 0 and say that's a predicted value of 0. So we'll have a nice two-class classification problem here. But in order to perform gradient descent, we need to be able to take the derivative of the activation function. So with some basic calculus, we know that the derivative of the sigmoid function is this, and you're welcome to derive this on your own using calculus, or if you don't have a lot of experience in calculus, that's perfectly fine as well. There are plenty of tutorials online that'll teach you the fundamentals of taking simple derivatives, such as this one. This is our predict function. This is responsible for taking our input data, taking the dot products, and then returning what our output prediction is going to be. So what we do here, this X data, that's our training data, our testing data, or the data we want to predict outputs for. And this W value, this is our weight matrix. This is the value that our model has actually learned during the gradient descent process. So to make a prediction, all we do is we take the sigmoid activation function, and then we're going to pass in the dot product between our data and our weight matrix. So take this dot product, pass it through the sigmoid activation, and you get these output predictions. Now we know these output predictions are going to lie in the range 0 to 1, but we need to threshold them at the 0.05 marker so that we know what class they belong to. That's what these two lines of code are doing. If the predicted value is less than or equal to 0.5, we'll clamp it down to 0. After that clamping process, if a value is greater than 0, then we also know by definition that it's greater than 0.5. So we'll clamp those values to 1. That's what these two lines of code are doing. It's just taking this nice looking sigmoid function with a nice derivative and just turning it into a step function where anything below 0.5, that goes down to 0. A value greater than 0.5, that goes to 1. And then we'll return those predictions to the calling function. Let's move on to our command line arguments here. We have the number of epochs. This is the number of times that our model can see the training data. Updating our weight matrix is going to be an iterative process. It's not like importing, a library like say your support vector machine library from scikit-learn and passing in the data and then does these projections in higher dimensional spaces and only has to look at the data once and that type of operation. That's not how gradient descent and neural networks work. Instead, what happens is that we train our model in the concept of epochs, and an epoch is defined by number of times our model has seen the entirety of our training data. So with what we're telling our command line argument here is that we're going to allow our model to see the training data, the complete entire data set of training data, a total of 100 times. So it's going to have 100 chances to iteratively improve itself. Then we have this alpha value, which is called our learning rate. And once we start discussing neural networks in more detail, you're going to learn that tuning this learning rate is just a royal pain. And that's where you're going to spend the vast majority of your time when you're training your neural networks. It's trying to get a really good value for your learning rate such that your model can learn. If you set your learning rate too high, then your model is just gonna be bouncing around. It's like taking too much caffeine. It's like having too much coffee or too much tea when you're trying to focus on a really challenging task. There's that sweet spot of caffeine that keeps you focused on it. But if you have too much caffeine, then you're just bouncing all around the walls. You can't focus. Like your brain wants to switch from task to task to task. It can't focus on what is right in front of you. If your learning rate is too low, then that's like trying to get really hard work done on 2 hours of sleep. You're not going to be able to focus. Your brain is going to be sluggish. You're going to be moving slowly. You're not going to be making these important, intelligent connections, and you're not going to get your work done. That's essentially a good parallel and a good analogy to what a learning rate is in terms of gradient descent and neural networks. If you set this value too high, then you're going to spend all your time bouncing around and you're not going to learn anything from the underlying patterns. If you set the value too low, then you're not going to develop this momentum to be able to start rolling down the gradient descent hill and learn the important patterns. You're just going to make tiny little incremental improvements, and it's going to take forever to reach a reasonable, accurate prediction if you can ever get there at all. Typical learning rate values here are 0.01. You'll see 0.1 at times. You'll see 0.001 and then 0.0001. We typically tune these values based off of an order of magnitude because that's generally where you see the improvements on within those order of magnitude jumps. Anything less than that, you could see an improvement, but it's not going to be as pronounced. So there's tons of algorithms. It's called hyperparameter tuning around tuning your learning rate. For these examples, don't worry about that too much. I've provided an initial learning rate that'll show you the results. And as we get further and further in this course, you'll learn how to select a learning rate yourself. Here is where we create our data set. We're going to generate a total of 1,000 data points. It's going to be a 2D data set, so these are going to be our XY coordinates. There's going to be two centers, so there's going to be two classes. And this is the standard deviation of each data point within each blob. And then this random state here, this is just used for reproducibility. So when we run this line of code, you're going to get this data set right here. We're going to have two blobs, which is specified by the number of centers. We're going to have two features, and that makes sense because one is the x coordinate and one is the y coordinate. We have the standard deviation here. So, if the mean is right around here, then that gives us this 1.5 standard deviation. And same thing here. Here is probably our mean, and then our standard deviation allows these points to fall within that distribution. We know we have these 2D data points in this x variable, and then the y variable is either 0 or 1, depending on whether it belongs to the purple blob or the yellow blob. That's what we're doing here is we're reshaping this into just a single flattened vector. Now here's our bias trick, and I talk about the bias trick inside the text version of this article, which is why it's so important that you go through this. But the gist here is that we can define our prediction function in terms of f of x equals our weight matrix dot product with each individual x sample plus the bias. That additional bias term can actually be rewritten as a single dot product by embedding a column of ones to our input data. So that's what we're actually doing here. We insert a column of ones as the last entry in the feature matrix. You could put this at this column of ones as the first entry, as the last entry, as the second entry, as the 100th entry. Doesn't really matter, provided that it exists, that there's this constant value, this constant column of ones somewhere inside your input data. So that's all this line of code is doing. It's just inserting that column of ones inside the training data. So once we've done that, we'll create our training and testing splits. So this is the training data. This is the testing XY coordinates. This is the training labels, either 0 or 1, and these are the testing labels, either 0 or 1. So we'll use 50% of our data here for training and 50% for testing. Now it's time to actually learn this weight matrix. So we're going to generate a random numbers, and there's all types of literature in the computer science and neural network community and deep learning community that you can read about on how to properly initialize a weight matrix such that we'll have a better chance of converging and reaching an optimal solution. But for us, we'll be using a standard normal distribution. And right here, we're going to have the number of rows is going to be equal to the number of columns in our data set, and then we're going to have one column here. So that's what this dot product here is doing here, is we have our weight matrix. We're going to take the dot product and then add in the bias, but using our bias trick, it's actually far simpler because we have our weight matrix dotted with this each individual X sample, and then that one here makes that entire process easier. It makes that this B term redundant since we've embedded it right over here. Here is where we start actually learning. So we're going to loop over all 100 epochs. We're going to take the training data and dot it with our weight matrix and pass that through our sigmoid activation function. That's going to give us our predictions, which is going to be a continuous value in the range of 0 to 1, which is the output of our sigmoid activation function. So after running this line of code, we'll have predictions for every one of our data points in the range 0 to 1. So let's look at the error. The error here is going to be taking the predictions in the range 0 to 1 and subtracting them from our class labels. I'll open up a Python shell just to make this a little more clear. But let's say that our predicted value is 0.75 and our true class label on train Y is equal to 1. Well, that's the difference between prediction and the label is negative 0.25. So that shows us how off we were. That's the concept of a loss. How quote unquote incorrect were we in making that prediction? Or you could, if you're a glass half full person, I guess you could say, how correct were we in making that prediction? Now, let's say that the true class label was a 0, and we get prediction minus the label. That's 0.75. And if both the prediction and the label are the same, then the error, the loss here is 0. That means that we did not make a mistake. We were correct in our predictions. So the loss here is going to be the sum of the squared errors. So for each error term, we're going to square it, and then we're going to take the sum of those values, and that's going to be the loss value for this current epoch. We'll monitor the loss, and our goal, again, is to drive the loss as low as possible. That's the concept of gradient descent. We want, with each iteration, with each epoch, with each update of our weight matrix, we want this loss descend nice and slow. We want to get a nice smooth graph of our loss descending, indicating we're descending into lower losses of the loss landscape, where ideally we're making correct predictions. So here is the true gradient descent process. We have our predictions. Let's pass them through our sigmoid derivative function and then multiply them by our error. To get the gradient value itself, we take the training data, transpose it so that the dimensions of the matrices align. I'll take the dot product, passing in this d value, which is again measuring our error. So this gradient is telling us, okay, we're on this slope right now. And if we look at it in terms of an actual plot, then you could say, all right, we're here. Where we want to be is down here, but we're up here. This gradient value is actually pointing up right now. We wanted to get to point it down so that we could start slowly coming down this loss landscape and descend into lower areas of the loss landscape. That's why you see this negative term in our weight update, because this gradient is kind of facing up this way. We want to take a step in the opposite of that direction, hence the term gradient descent, because we want to go down. So that's why we're taking that step. So the weight matrix is updated by adding in the negative alpha value times the gradient. This is our learning rate, remember. If this learning rate is too large, or if we don't use a learning rate value at all, then what happens is that this gradient update could be so large that we go from here over to here. And then we totally miss this minimum area that we want to descend in. So we use a small value. So we could start here, take a small step at epoch 1, epoch 2, we'll take another step, and we'll iteratively apply this process until eventually we end up in the lowest area of the loss landscape. So that's essentially what this code is doing. And nearly all training procedures under the hood, if you look at the underlying implementation of gradient descent in neural networks and deep neural networks, this is really what you're doing. Yeah, there's certain additional bells and whistles you can apply, and we'll discuss that when we start talking about stochastic gradient descent and mini batch gradient descent and regularization terms. But all of them more or less follow this training procedure of, okay, we have a weight matrix, and then we have this input data. Let's make predictions on the input data by taking the dot product between the input data and our weight matrix. All right, now we have the predictions. Let's compute our error, see how off our predictions were. Then we'll compute the derivative of the predictions, then multiply by our error, and then that's where we derive our gradient from. Once we have the gradient, this is our actual weight update steps. This is where the true learning comes from. This is where we're updating our weight matrix, and keep in mind that our weight matrix has the bias vector embedded into it. So this is where the learning takes place. This is where the true gradient descent takes place. Once we've iterated over our data a total of 100 times, then what we'll do is make predictions using our testing set. So this is data that our model has never seen before. We want to test the ability of our model to generalize to data it hasn't seen. So we'll pass in our testing data and our learned weight matrix, and we'll show a classification report to demonstrate that our model has in fact learned something. And then for visualization purposes, we'll display our input data, the data that we're learning from, as well as a plot showing our loss over the course of the epochs. Ideally, what we'll see is our loss starting off high and then descending lower into areas of the loss landscape. So let's run this script again now that we have this additional knowledge. And again, here is the data that we've generated. We have two classes. This is our yellow data set, and this is our purple data set. And then our goal was to be able to learn essentially a linear separator between these two. So if we imagine this line drawn between the data set that splits the two classes, if a data point resides on this part of the line, then we're going to say this is part of the yellow class. And if it resides on this side of the imaginary line, then it belongs to the purple class. When we run our script, notice what's happening here. We have a really, really high loss value to start off. That means we're making a lot of incorrect predictions. But pretty quickly, by the time we've got the epoch 5, we're getting really, really good at making predictions. And if you track these values, you'll see that after each and every epoch, loss is continuing to decrease. That is a really good sign because it implies that our model is learning the underlying pattern in the data set itself. So when you train neural networks on your own data sets, yeah, you're going to see your loss start off really high. But what you hope to see is that after each and every step, after each time you update the weights to your neural network, it gets better at making those predictions. So by the time we get to our classification report, we're getting 100% accuracy. For any given data point in our testing set, we're able to correctly predict, hey, does this belong to the yellow blob or does this belong to the purple blob? That is the essence of gradient descent. It's an optimization algorithm. It says, given this weight matrix W and our input data, let's iteratively update our weight matrix such that it gets better and better and better at making predictions. It's a slower process for sure because it requires the neural network or the model or the weight optimizer to see our training data multiple times. This is unlike other types of machine learning algorithms that could be pretty quick. But luckily, with GPU accelerated hardware, it's become possible to train really deep neural networks on super large data sets, all using algorithms based off of gradient descent. This is a vanilla version of gradient descent where we're making predictions on our entire input data set at once and then updating our weight matrix. That is fine for small data sets. but it doesn't really work for large data sets that have thousands of images, tens of thousands of images, or millions of images, because that means that to perform one single epoch, we have to make predictions on all of that input data at once, and then we got to update our weight matrix. So if we have a data set with a million images, we're not performing any weight updates until all 1 million images are processed at once. It turns out that's pretty computationally wasteful. And instead, we could trivially make a prediction on just one of those input data points and then update our weight matrix based off of the loss of that one image. So that means instead of having to loop over 1 million images in order to make one singular step in a better direction in order to make better predictions, that means for a million images, we have a million chances in a single epoch to update the weights of the model. It's a little bit messier. Our model is going to make a little more errors initially, but what's really nice about this approach is it scales really well. And then it scales even better when we start creating what's called mini batches. So instead of just trivially making predictions on one image and then updating our weight matrix, what we would end up doing instead is like gathering batches of say 60 or 32 images or 64, 128 or 256, and then treating that as the input here versus just one data point or the entire training set. So doing that will average out some of the noise and will make much better, more quote unquote intelligent updates to our weight matrix. Those classes of algorithms are, mini batch gradient descent, stochastic gradient descent. They're going to be the topic of our next two lessons. But for now, now that you've gotten to the end of this lesson, I'll assume you have read the text version of this article once. I now want you to go back, finish up this video, and then go back and read the text version of this article again, now that you've gotten a more detailed explanation of the code. Again, all of deep neural networks, all of neural networks in general, is powered by gradient descent. If you have $1 to spend at the neural network store, you should spend 85 to 90 cents of that dollar learning about gradient descent, especially if you're a beginner. This is such a key concept in neural networks. Don't keep continuing on in the course until you understand this concept. I'll see you next time when we start digging into stochastic gradient descent.